Hi, my name is Devlina and today I'll be talking about our work, Semantic-Based Explainable AI, Leveraging Semantic Scene Graphs and Pairwise Ranking to Explain Robot Failures. In present day, robots are increasingly being deployed to work in human environments to accomplish complex tasks. And while these robots are successful in executing these tasks, unexpected failures can be inevitable and may require human assistance for recovery. Yet, in most cases, the co-located users are not AI experts or roboticists, and without an explanation from the robot, cannot understand the cause of failure. This leads us to our main research question. Given a situation where the robot encounters a failure that causes it to halt its task execution, how can we autonomously extract contextual information from an environment to explain robot failures to everyday users? Our work relates to prior work across multiple areas. In the first domain of explainable AI, most of the work focuses on understanding the outputs of deep learning models. Traditionally, these models have mainly focused on single classification tasks, and the explanations have been aimed at AI experts. More closely related to robotics, the subfield of explainable AI planning has focused on explaining sequential decision-making tasks. Most prior work in this area has focused on explaining why one planned solution is more preferable than another. In the domain of semantic scene graphs, there's been a lot of work that investigates how to capture relationships between objects in a scene for higher level visual understanding and reasoning tasks. These include image or video captioning or visual question answering. In fault diagnosis literature, a number of techniques have been developed for robot failure recoveries, but these systems are aimed at software developers or expert operators. And finally, recent work in AI has demonstrated that human-centered explanations in the form of context-based explanations can improve user confidence in systems as well as improve their understanding of system failures. However, these early works lack generalizable techniques given their need to hand annotate the contextual information a priori to explain each situation of interest. We build on the findings of the shown research areas here. Specifically, our work lies at the intersection of these areas, and we generate semantic-based explanations by leveraging scene graphs to autonomously extract the semantic information in a failure scene. Now, by leveraging scene graphs, our semantic-based explanations can expand the current scope of failures that are explainable to everyday users. In our work, we expand the set of failure scenarios we can explain in comparison to prior work across two dimensions: the cause of failure, which is denoted here by f sub c, as well as the failure type, which is denoted here by f sub t. Existing context-based explanations can explain the three spatial failures shown here in light blue for failures that are caused by a single failure. In our work, leveraging scene graphs allows to increase the set of failure causes we can explain. Specifically in this work, we can develop explanations for additional spatial-related causes as well as attribute-related causes. We also investigate the instances of compound failures, where the failure may be caused by more than one spatial failure or say a combination of spatial and attribute-related failures. And these set of failure types and failure causes have not been explainable by prior work. So given the increased scope of failures that we can explain by leveraging the semantic information from a scene, we first investigate whether users actually prefer these semantic-based explanations compared to the existing context-based explanations for understanding robot failures. So to determine user preferences between prior context-based explanations and our semantic-based explanations, we conducted a within-subjects user study in which participants were presented with 34 images of robot pick failures in the home environment. They were also provided with hand-scripted explanations of both the semantic and context-based explanations. Their task was to select which explanation was the most helpful in helping them understand the cause of failure. Here on the left, we show the user's perceived helpfulness of each explanation type across all the aggregated failure types. The results show that overall, users prefer the semantic-based explanations significantly more than the context-based explanations. Furthermore, when examining each failure type individually, we see that for all failure types, users significantly preferred the semantic-based explanations over context-based explanations again. So in other words, the results of this study really validate that explanations grounded in inter-object relations and object attributes are significantly more useful to everyday users. So given the importance of these semantic-based explanations, we contribute the following semantic explanation framework for autonomously generating these explanations. In our framework, a state-of-the-art semantic scene graph algorithm MotifNet is adapted to autonomously capture the semantic relations and attributes in a scene from the robot's point of view. We then leverage pairwise ranking to autonomously place attention to only the relevant relations that contribute to a given failure, and this allows us to generate explanations that are failure-focused. So our framework can produce two types of explanations: the unranked semantic explanations known as SSG and highlighted here in yellow, as well as the ranked semantic explanations known as SSG-R, which are highlighted here in green. So to extract the semantic information from a scene, we adapt the scene graph model MotifNet shown here on the left. Given an image I with detected objects O sub I through O sub j and corresponding bounding boxes B sub I through B sub j, we utilize the bidirectional LSTMs with highway connections from the original MotifNet model to extract the global context D of each bounding region in the image. The global context in conjunction with the union of bounding box regions are then utilized to predict the relationships R sub 1 through R sub k, where each relationship is made up of the object names, associated object attributes, as well as the predicate relationships between these objects. So for example, the algorithm can produce book underneath heavy laptop or book on table. To train our model, we collected 188 failure scenarios from AI2Thor, which represented the point of view of the robot as it attempted to pick up the desired object. Now, 126 of these images were used for training, 32 were used for validation, and 32 were used for evaluation. For our application purposes, we focus on the scene graph task of predicate classification. That is, given the ground truth object labels and the ground truth bounding box labels, we utilize MotifNet to predict the predicate relationships between two corresponding objects. As you can see here by the true positive rates, our model does fairly well in generalizing the predicate relationships. However, seen here by the yellow sections, we acknowledge that the model has room to improve, and we suspect that with additional training data, the model can better differentiate these predicate relations with even greater accuracy. Now, to generate the natural language explanations from the outputs of the scene graph model, we take a template-based approach. Specifically, we extract a subgraph G from our scene graph to include all relations that contain the desired object in the relation. So in this manner, we can generate explanations such as the robot cannot pick up the desired object because of reasoning, where reasoning is replaced with all relationships in the subgraph small g. From these examples here, we can qualitatively see that the semantic-based SSG explanations are much richer in content than the context-based ones. However, when we read more closely, we realize that the semantic-based SSG explanations contain extraneous information. Ideally, we'd like to produce these types of explanations, SSG-R, which only contain the true cause of failure. Therefore, to generate these SSG-R failure-focused explanations, we leverage pairwise ranking, where each relationship in subgraph G is ranked by the relevance to the cause of failure. On the right here, we summarize the workings of the pairwise ranking algorithm. Let f sub m and f sub k represent the feature vectors for their corresponding relationships r sub k and r sub m that we wish to rank. A feature vector such as f sub k is made up of e sub ij, a sub ik, and a sub jk, which represent the predicate relation between two objects o sub I and o sub j, the attribute of the object o sub I, and the attribute of the object o sub j. Now, we utilize the predicate relations and the attribute information of objects as features since they define the core properties within a relationship. So we can then compare these feature vectors to reason about which properties in a relationship are more indicative of a failure in comparison to the properties of another relationship. So two comparing feature vectors are then passed through three binary random forest classifiers, which represent the three different combinations of three binary label pairs. The classifier outputs predicted labels y sub km, which can be a value of 0, 1, or 2 depending on whether the properties of one relationship is more relevant than describing the failure than the other, or if they're equally of value in describing the failure. The ranking logic then uses these predicted labels to rank the features accordingly, and in this manner we can extract the top relevant relations from the ranked list of all relations in subgraph G. So given that we can generate both the semantic-based SSG explanations as well as the semantic-based but failure-focused SSG-R explanations, the next question to answer is, well, how do these model-generated semantic-based explanations compare to their ground truth versions, as well as how do they compare to prior work in helping users identify failures and assist in failure recovery? So to compare how effective each explanation type is in helping our users, we conducted an additional user study where we recruited 90 participants from Amazon Mechanical Turk. There were 15 participants in each study condition, and each participant was shown images of failure scenarios from the robot's point of view when it encountered a failure. The participants were then asked to identify the cause of failure and provide a solution to the failure for robot recovery. The user study was broken up into two stages to be able to see the impact of an explanation. So in the pre-stage, users saw 16 failure scenarios with no provided explanations, and in the explanation stage, users saw 16 more failure scenarios, this time with explanations provided from their study condition. And the intuition for this two-stage study was to first establish the participants' baseline understanding and then measure the effect an explanation had on improving their understanding. So to measure this improvement, we had two metrics, failure identification and solution identification, which measured their abilities to correctly identify a failure cause as well as identify a solution. Both of these metrics were then calculated by the average F1 score difference between the two stages. So using these metrics, we first analyzed how participants' failure identification performance compared across each explanation type. And from the graph on the left here, we can see that the SSG-R explanations significantly improved users' failure identification compared to the unranked SSG explanations, as well as prior work's CB explanations. When examining participants' solution identification performance, we see similar trends here as well. SSG-R explanations significantly improved solution identification compared to both prior work CB explanations as well as the unranked SSG explanations. So overall, these results demonstrate the importance failure-focused explanations have in helping users gauge the cause of a robot's failure as well as how to help the robot recover. Now, for more details on these results as well as the analysis of each failure type individually, please see our paper. So in summary, we show that semantically descriptive explanations are significantly preferable by everyday users for failure understanding compared to the context-based explanations in prior work. We also show how leveraging pairwise ranking to autonomously extract the relevant reasoning for failures can produce more failure-focused explanations. And finally, we show that our semantic explanation framework can generate explanations that improve both the user's ability to identify failures as well as suggest accurate failure recoveries. And with that, I'd like to thank you all for listening.